In this video, we shall be solving the questions from Ncert textbook. The chapter is Moving Charges and Magnetism. The total number of questions which we are going to have here today is 1 to 13. So let us solve them one by one. Question number 1 is saying the circular coil of wire consisting of 100 turns, each of radius 8 cm, carries a current of 0.40 ampere. What is the magnitude of the magnetic field B at the center? This is the circular coil if you are going to consider having many turns, like as in the question it is saying it is containing 100 turns. So let us take N is equal to 100, R is equal to 8 cm, and the current which is being taken across the coil is 0.40 ampere. So the formula which we are going to have to get the field at the center of this particular circular coil is mu naught I upon 2R. For a single turn, if we multiply by N, it would be field due to whole circular coil. Put all the values. N is 100, mu value is 4 pi into 10 raised to minus 7, I is 0.40 ampere, and 2, then R is 8 centimeter. We have to change into meter. After getting this calculation, we would be having B, that is magnetic field at the center, is 3.14 into 10 raised to minus 4 Tesla. Question number 2. A long straight wire carries a current of 35 ampere. What is the magnetic field at a point 20 centimeter from the wire? So this is the wire having a current 35 ampere. We have to find the magnetic field at a distance 20 centimeter. Now we have to calculate magnitude only. The formula for the magnitude of magnetic field is mu naught upon 4 pi 2I upon R. Mu naught upon 4 pi is 10 raised to minus 7. 2, value of I is 35 ampere and distance is 0.2 meter. After simplifying it, we would be having B as 3.5 into 10 raised to minus 5 Tesla. In this question, it is saying that a long straight wire in the horizontal plane carries a current 50 ampere in north-south direction. Let us take first the direction on the screen, and then to get the wire here, we are going to have the current 50 ampere as given in the question from north to south direction. We have to calculate the magnitude of a field as well as direction of the field at a distance 2.5 meter in direction east from the wire. So with the given value, if we calculate the field as per the formula is mu naught upon 4 pi 2I upon R, we put all the values. After calculation, we will be getting B as 4 into 10 raised to minus 6 Tesla. And this, if we apply Maxwell right hand screw law, the direction would come as vertically downward direction. Question number 4.4 is saying a horizontal overhead power line carries a current 90 ampere. This kind of wire we can see which is carrying a current 90 ampere in east to west direction. Again, we will take the direction of the current from east to west. The current amount is 90 ampere and we have to calculate the field at a distance 1.5 meter below the power cable line. So this is the perpendicular below, that is perpendicular downward in 3D concept you can understand. It is 1.5 meter from the power cable. If we take the given values, it is 90 ampere current, distance is 1.5 meter. Formula remains the same as mu naught upon 4 pi 2I upon R. We put all the values and after calculation we will be getting 120 into 10 raised to minus 7 or 1.2 into 10 raised to minus 5 Tesla. And the direction is as per the Maxwell right hand screw law, we can get it as towards south direction. Question number 5 is saying what is the magnitude of magnetic force per unit length on a wire carrying a current 8 ampere and makes an angle 30 degree with the direction of uniform magnetic field 0.15 Tesla. So this is the magnetic field. A wire carrying some amount of current is placed in the magnetic field at an angle 30 degree, and the given value we take I is equal to 8 ampere, B is equal to 0.15 Tesla, and the angle is 30 degree. Again, if we want to apply the formula of force acting on a current carrying conductor, straight current carrying conductor in magnetic field, it is nothing but F is equal to I into L into B sine theta, or IL cross B. So I is the current, L is the length of the conductor, B is the magnetic field in which it is placed, and angle is the angle or inclination between the wire and the field. But in the question it is being asked, find the magnetic force per unit length. So force per unit length, if you are going to take, L would get cancelled and it is coming IB sine theta. So value of I is 8 ampere, then B is 0.15, sine 30 is nothing but half. After multiplication and calculation we will be getting 0.6 Newton per meter. Question number 6, it's saying that a 3 centimeter wire carrying a current of 10 ampere is placed inside a solenoid perpendicular to its axis. So this is the solenoid, and we know that some field would be generating inside the solenoid because of the current. That field is directly given in the question as the magnitude. The magnetic field inside the solenoid is given to be 0.27 Tesla. What is the magnetic force on the wire? This is the wire kept perpendicular to the field of the solenoid. Current is given 10 ampere. B, which is getting generated inside the solenoid, is already given 0.25 Tesla. Then we have to calculate what is the force on the wire having length 3 centimeter, which is placed perpendicular to the axis of the dipole. It means angle is 90 degree. Then formula is again remains the same as we have used in question number 5, that is F is equal to ILB sine theta. I is 10 ampere, length is 3 centimeter, so 3 into 10 raised to minus 2 meter. Then B is 0.27 Tesla, and sine 90 is 1. After multiplication this, we will be getting 0.081 Newton. In this question, saying that two long and parallel straight wires A and B carrying current 8 ampere and 5 ampere in the same direction, and the separation between them is given 4 centimeter. We have to find the force on a section of 10 centimeter on wire A. So here is the 10 centimeter section on wire A. First we need to know what is the force on a particular length between two parallel current carrying conductor, and it is mu naught upon 4 pi to I1 I2 R, I1 I2 upon R into L. That L is the length of smaller section between these two. Here L is given 10 centimeter. If we put all the values like mu naught upon 4 pi 10 raised to minus 7, 2, I1 is 8, I2 is 5, and then upon R is 4 centi would be changed into meter, 4 into 10 raised to minus 2, and then length again would be changed to 10, that is 10 into 10 raised to minus 2 meter. 10 raised to minus 2 would get cancelled, and after simplifying it we would be getting the value of force as 2 into 10 raised to minus 5 Newton, and obviously it would be attractive in nature. Then question number 8 is saying that a closely wound solenoid 80 centimeter has 5 layers of windings of 400 turns each. That 400 turns each, but 5 layers are there. So if we are having 5 layers, total number of turns if you want to find, it would be 5 into 400, that is 2000 turns. But these 2000 turns are available in 0.8 meter, that is 80 centimeter. So what is number of turns per unit length? Then we have to divide by the length. It means it is 2500 per meter. 2500, that is 2500 per meter. The question is, estimate the magnitude of B inside the solenoid near its center. We know that the field inside the solenoid near its center would be B is equal to mu naught Ni, where N is the number of turns per unit length. So it is mu naught 4 pi 10 raised to minus 7, N is 2500, and current is 8 ampere. After multiplying or simplify them, we will be getting 8 pi into 10 raised to minus 3 Tesla. If we multiply pi, that is 3.14 into 8, we will be getting 2.25 into 10 raised to minus 2 Tesla. Then question number 9. There is a square coil of side 10 centimeter, consists of 20 turns and carries a current of 12 ampere. So number of turns we have 20 and the current is 12 ampere. The coil is suspended vertically in the normal to the plane of the coil, makes an angle 30 degree with the direction of uniform horizontal magnetic field of magnitude 0.80 Tesla. What is the magnitude of torque experienced by the coil. So suppose this is the coil placed in angle 30 degree, and the other values which we can have here, its side is 0.1 meter, so area would be 0.01 or 10 raised to minus 2 meters square, and then the area would be 10 raised to minus 2 meters square, and then n number of turns 20, I is equal to 12 ampere, angle is 30 degree, and then the magnetic field in which it is placed is 0.80 Tesla. If we apply the formula of torque, that is nothing but N into I into A B sine theta, we put all the values, and after simplifying them, we will be getting 0.96 Newton meter. Question number 10, we have 2 meters moving coil galvanometers M1 and M2, and the particulars are given here. R1 is equal to 10 ohm, N1 is equal to, that is number of turns, 30, area is 3.6 into 10 raised to minus 3, the area enclosed by the coil is given, and then for first meter the magnetic field is given, and all the particulars are given for the second meter as well. The question is, we have to find the ratio of current sensitivity and voltage sensitivity of meter 2 with respect to meter 1. So now let us first see the formula of current sensitivity. It is nothing but deflection per unit current, and it is NBA upon K, where N is the number of turns, B is the magnetic field in which the magnetic field which is being produced by the magnets in the moving coil, A is the area enclosed by the coil, K is the spring constant. So K is constant, the spring constant is identical for both the meters. So we are taking that I dash S, that is the current sensitivity of meter 2, with respect to IS, current sensitivity of meter 1, as N2 B2 A2 upon K upon N1 B1 A1 upon K. So K would get cancelled, and it is N2 B2 A2 upon N1 B1 A1. We put all the values, and after calculation we will be getting 42 upon 30 or 7 upon 5 or 1.2. Then if we talk about voltage sensitivity, the formula is nothing but IV is equal to phi upon I into R. So NBA upon K into R, where R is the resistance. If we take the ratio, that voltage sensitivity of second with respect to first, it is R2, and R1 would be additional than the previous one. So after simplifying, because K and K is getting cancelled, it is R1 upon R2 into, we can write the current sensitivity which we have received in the previous calculation. So after getting that, 7 upon 5 into R1 upon R2 is 10 upon 14, we will be getting it as 1. So voltage sensitivity ratio is 1, current sensitivity is 7 upon 5. Here you can see current sensitivity is different, but voltage sensitivity is not getting changed. Now question number 11 is, in a chamber, a uniform magnetic field 6.5 Gauss is maintained. An electron is shot into the field with a speed of 4.8 into 10 raised to 6 meter per second normal to the field. Explain why the path of electron is circle. Determine the ratio of orbit. So what all things are given? First, field is given 6.5 Gauss. We know that Gauss is not the SI unit, it is the CGS unit. If you want to change, 1 Gauss is equal to 10 raised to minus 4 Tesla as given in the question itself. Then velocity is given 4.8 into 10 raised to 6 meter per second, and then angle is given 90 degree because it is shot perpendicular to the magnetic field or normal to the magnetic field. Here, why it is acquiring a circular path? Because force, that is electric force, acting on charged particle actually appearing as centripetal force. And we know that whenever centripetal force develops in a body, it starts moving on a circular path. So here, if we take the mathematical formula QVB sine theta is equal to mv square upon r. Because 90 degrees, so it will be 1, and then it will be r is equal to mv square upon QVB sine theta. Here r is equal to mv upon qv sine 90 degree, or sine 90 is 1, so we can take mv upon qb. Now m is nothing but mass of electron, v is velocity of electron, q is charge on electron, and then b is the existing magnetic field given over there. We put all the values, we calculate it and adjust the power of 10, we will be getting as 4.2 into 10 raised to minus 2 meter or 4.2 centimeter, which is the radius procured by the electron during its motion. Question number 12 is asking that in exercise 4.11, obtain the frequency of a revolution of electron in its circular orbit. Does the answer depend on the speed of the electron? So look at the formula which we are going to get here is, first this is the circular path and this is the radius r. We have to find the frequency. Frequency means number of revolution in 1 second. So if we want to first find the time period, it is nothing but total distance covered by the speed, that is 2 pi r in one round, and the speed is v, that is given in the question, 4.8 into 10 raised to 6. So frequency is nothing but reciprocal to the time period, it is v upon 2 pi r. We put value 4.8 into 10 raised to 6 as velocity, and you can see here that the answer does depend upon the velocity. F is equal to v upon 2 pi r. So F is equal to 4.8 into 10 raised to 6 upon 2 into pi, that is 22 upon 7. 4.2 into 10 raised to minus 2 is the radius. So once we simplify it, we will be getting as 4.22 into 10 raised to 8 or 0.181 into 10 raised to 8 or 18 megahertz is the frequency. Question number 13 is saying that a circular coil of 30 turns and radius 8 centimeter carrying a current 6 ampere is suspended vertically in a uniform horizontal magnetic field of magnitude 1 Tesla. So this is the magnitude, this is the magnetic field having magnitude 0.1 Tesla, and this is the coil having 30 turns which are placed here, and the current flowing is 6 ampere. The question is, calculate the magnetic field, calculate the magnitude of the counter torque that must be applied to prevent the coil from turning. We know that at equilibrium the counter torque applied by the particular field would be equal to the torque being experienced by the coil. So formula remains the same as per the given values. If you are going to take, it is placed the plane perpendicular to the axis is perpendicular to the magnetic field, so we are going to take theta is equal to 90 degree, and if we put here tau is equal to NIAB sin theta, area is pi r square, we put all the values, n is 30, I is 6, then pi is 3.14 and the radius is 8 centimeter whole square, and then b is 1 Tesla and then sin 60. So sin 60 value is root 3 by 2. After simplification we are going to get it as 3.13 Newton meter. B part is asking, would your answer change if the circular coil in A were replaced by a planar coil of some irregular shape that encloses the same area? If you see the torque, it does depend upon area, but it is not depending upon shape. So here torque remains the same. This is the solution of last question. Thanks for watching.